Yeah, uh, thank you very much for the kind introduction. Um, yeah, so I'm happy to take questions even during the talk if there's something unclear. And so I'm going to talk about variational Bayesian methods for autoregressive and recurrent models. And this, most importantly, is work with Dario Coscia. Um, and I should say he is the main architect of both the models and all the implementations, so all credit goes to him. So let's talk a little bit about a new paradigm shift that's happening in sort of, let's say, scientific applications, in particular molecular science. So in the old days, when people tried to discover a new material, they would just try a whole lot of things and then see what sticks. Um, and more recently, of course, people have started to analyze what comes out of experiments using statistical and machine learning methods. So a lot of data is collected, and then that data goes into a database, gets analyzed, and from there, new experiments are being designed. Now, the more recent thing even is that the experiments are even migrated as much as possible onto a digital device, a computer, which means that we actually simulate the laws of physics directly in the computer rather than doing the experiment. And of course, this requires a whole lot more of computational resources in order to do that. Um, but it is still much faster and cheaper than if you would actually have to do the experiment. And so this is the paradigm shift we are seeing. And so this means that we are going from experiment in a lab into sort of in silico simulation. But that's only one part of the sort of revolution that we're currently witnessing. The other one is we're going from simulation to emulation, and this has to do with AI. And so imagine you have a particular molecule that you're interested in, and you simulate it, let's say in a computer, because that's already, you've subscribed to the previous change. And so instead of doing the experiment in a test tube, you're doing as much as these experiments as possible inside a computer. Um, and now you come up with a better design. You think you have a better designed sort of molecule. And, usually you would then go and again go through the same set of, experiments in a computer to figure out, let's say, what the properties are of that particular material. And if it's better, you keep it. But what's happening right now is that not only sort of do we simulate these things in a computer, we then saving all the data of those simulations in a database. From those simulations, we're going to train machine learning models. And these machine learning models can either directly predict the properties that you would have obtained through a simulation, or they can accelerate the simulation itself. For instance, in molecular dynamics, this is called a machine learning force field. The force field, instead of having to go through quantum mechanical calculations or approximate quantum mechanical calculations, you then do the calculations through a machine learning force field. And this part, this part here we call a emulator, or sort of a surrogate. And instead of simulation, if you do it with a machine learning model, we call this emulation. So that together, I would say, is kind of the paradigm shift that we are witnessing. And then when I give a talk like this, I always get one question. Invariably, there's one question that everybody always asks. If you replace physics simulations with a surrogate that's trained machine learning model, can you trust it, right? So especially when you operate that surrogate outside of the regime where it was trained, um, can you still trust it? Yeah? So imagine you have a weather prediction um, algorithm. You can either run Navier-Stokes equations in order to predict the weather, tomorrow's weather, or you can run a machine learning surrogate. And recently there have been quite a few very successful surrogates for weather prediction because there is a lot of data in that domain. And The answer to that question is both extremely important as well as unclear. For instance, at some point, um, there was a heat wave in the United Kingdom, and people predicted it would go over 40 degrees or something like this. The weather prediction models and the machine learning models were predicting this. But if you then act on it, if you say tomorrow is going to be a heat wave and it's going to be over 40 degrees, the question is, should you evacuate people? Should you make sure people become prepared for that, which is actually expensive? Or should you, if you don't do anything and you make a mistake, then of course people might die or get injured. And so these are really life and death predictions, so now and then. And you really need to understand how confident you are of the prediction you're making. And for a physics model, you can have a lot more confidence in the predictions you're making, but even there, of course, this is an important question. But with machine learning models, more so even, especially as the climate is changing. As climate is changing, automatically you are starting to operate in regimes where you haven't seen data yet. And so you have to understand how well or how trustworthy your model is in this regime that you've not seen. And the answer to this, to me, at least the first part of the answer to this is we need to come up with trustworthy and computationally efficient uncertainty prediction. Now, in weather prediction, they know this very well, and they do ensembles. So they have slightly different models and slightly different initializations, and then they do many predictions, and then they just look at the sort of distribution of outcomes of that particular, of all of these simulations. Now, that's definitely a very good method, but ensembles are slow. And so you're going to pay a price for having to run many of these prediction algorithms. So what we will do in this work is to try to come up with a Bayesian method to make these predictions for these surrogates, and then also apply them to models in scientific applications. Okay, so I'll first say a few words about sequence models. So this is all about sequence models, and of course there's many sequence models because time is sequential. Of course, language models, large language models in particular, like ChatGPT, they are sequence models. They try to predict the next token or the next word in the sequence. And so if we manage to do this well in these, if we come up with a good Bayesian approach to predict uncertainty, it could actually become very important for these large language models. But there's also audio, and there's many other domains in which these sequence models play a very important role. Now, in particular in scientific models, and this is where I'm very interested in scientific applications, this plays a very important role. So let's look at, for instance, here, let's say weather prediction. And so we now have very good weather prediction models for, all sorts of hydrodynamical quantities in the atmosphere, such as wind speeds, temperature, pressure levels, um, moisture, whatever, right? Precipitation, all sorts of quantities that we want to predict about the weather. Also, we have a huge amount of data, and we currently there's a whole bunch of models that become as good as actually numerical integration of PDEs. But again, the criticism you often get is, how do you know they are good? And so then another class of models that I'm very interested in is molecules. And so you can think of a molecule also as a sequence. These are often called SMILE strings. So here's a SMILE representation of a molecule. So it's basically turning a graph into a one-dimensional sort of sequence model. And so now you can try to make predictions about these sequence models. And they typically have quite long-range interactions because when you open, let's say, a bracket here, you have to close it down the line. And so those represent quite long order correlations in these sequences. And they often are also related to these benzene rings here. And so here, for instance, we could want to generate a particular molecule with particular properties that we are interested in, or we may want to predict properties of a particular molecule by just giving it the sequence in the first place. And here's an example of, let's say, if we think about, let's say, models and how they can go wrong. So here's a language model. And the question here was, who holds the world record for crossing the Tiber River entirely on foot? And of course, we've all played with these language models and we've all found that they can be very confident in giving the wrong answer. So here the answer is the world record for crossing the Tiber River entirely on foot was set by Michael Van Page, a British mixed martial arts kickboxer, blah, blah, blah. Page performed this incredible feat by running on water across the river using floating shoes. It's hard to figure out where I got this from, but it's very confident to tell you that, this guy ran on water on floating shoes. And so what we ideally want is that this particular algorithm would have an internal measure of how uncertain it would be about this. And, there might have been a bullshit kind of measure here, which would say, I'm saying this, but actually I know this is likely nonsense, right? That would actually be very useful. And here is a PDE solver. Below here is, one of the two, I forget which one, is the true with a numerical solver. And this is probably the one with the coming from the machine learning model. And you can see that for a while, it's very good, and both models are very much on track. But there will be a time when they start diverging, and you can sort of see here at this regime here that here these things start to merge, where in this one they merge much later, and so here there is a divergence. And so that will be a signal that the accuracy is coming down, and you would want a method that detects that, here it's very confident, everything is good, and here it detects all by itself that the solution that the machine learning model gives is indeed becoming uncertain. And we will see that that's exactly what the model that we propose is able to do. Now, this is a statistics group, I think, and so you're probably all familiar with Bayesian statistics. This is one approach that is particularly good to also model epistemic uncertainty, which is the uncertainty in the parameters of the model. It's a very elegant approach. So one question you could ask, why is not everybody using it in this deep learning and LLM space? And the reason is that it is typically, it could actually hurt predictive performance, and it's typically slow. And so in this work, we actually want to show that that's not necessarily the case. You can build models that are not less predictive, even in the context of deep learning and deep neural networks, and have reliable uncertainty prediction, and at a very high efficiency. So we don't have to, we don't have to be much slower and less efficient in terms of compute for these models. And so the idea is that, over time, we would want a curve like this, where we have the actual prediction, but we also have an increased uncertainty typically as time progresses, so that we get a sense of how much we can trust this prediction. And one other part that's interesting is that in large language models, there is a method that's called RLHF, which is reinforcement learning with human feedback. And you can think of that method as sort of a Bayesian method, according to this paper. RL with KL penalties is better viewed as Bayesian inference, where you kind of reweight, in some sense, the probabilities of a particular outcome. You just reweight them with your sort of human feedback. And so the approach that we're going to take here is, I guess there's two main approaches, main categories of methods that people use in Bayesian statistics, or at least inference in Bayesian statistics, which one is Markov chain Monte Carlo. That's not the one that we'll be using here. We'll be using a version of variational Bayesian inference. Now, how does that work, variational Bayesian inference? So you have some true posterior distribution. That's the blue one. You might not know it, but you typically know the likelihood and the prior. So you might not know the normalization constant, but you typically know the likelihood PD given omega and the prior P omega. And then what we're going to do is we're going to fit a distribution, a posterior, variational posterior distribution to this exact posterior distribution within a tractable class of distributions. Q, this could be Gaussians, or could be mean field distributions, or a tractable class, by minimizing the Kullbaum-Leibler divergence between the variational distribution and the actual true ground truth distribution. And you could ask, how is that possible? Because you don't know P precisely, because you don't know the normalization constant, but the good fortune is that you can write it as this object, as log P of data, which is the normalization constant, and this one is constant. And then what's left over is this piece. And it turns out this creates a bound on the scale, an upper bound on the scale. And it is the expectation of this object, which we know, because this is P of D given omega times P of omega. And then the expectation over the variational posterior minus an entropy term. And the entropy term is completely in terms of our variational distribution, and so it's tractable as well. And so now we're just going to minimize this particular bound over Q, and that will give us the approximation that we need. Now, the question always is, what prior should I be using in a neural net? Just like a very high dimensional problem. We have millions, if not billions, of parameters in these networks. And so we need to come up with some prior distribution, which makes some sense. At the same time, we also need to remain efficient so that we can run these procedures about the same speed as we would run a normal forward pass through a neural network. And we need to come up with a prior and efficiency is really important. So we're going to take a class of distributions, variational distributions, as normal distributions. And then there's this trick, which we reported here already a long time ago, variational dropout and the local reparameterization trick. And what it does is it integrates out the variables over the parameters of the layer. And it's because it's Gaussian, you can do it. And then the noise that's sitting in these parameters here is migrated to the latent variables in the next layer. So in principle, given the parameters, it's a deterministic update as you go through these layers. But the parameters are now noisy because they're random variables. And now we integrate them out. And that means that the noise of the randomness of these parameters is now going to reside in the latent variables. And so what we are now going to focus on the posterior distribution of Y, which is the activations of the next layer given the previous layer, given X, where the omegas are integrated out. And that you can do exactly, and that's going to be a normal distribution, X times the mean of the parameters omega. And then here is the noise is correlated noise over the random variables Y. Now this can actually be quite expensive, and so we also now apply a trick to make this less expensive. So the model we propose with these co-authors, and again, Dario is the first author here. The model we propose is called BARNN. It's a Bayesian autoregressive and recurrent neural network. So it can apply to any recurrent neural network, including LSTMs and all these things, as we will see. And the model looks like this. I'll go into a little bit more detail here in a minute, going over these pictures. And sort of here you can sort of see an execution of this algorithm. So the blue line is the mean forecast. And then you can sort of see a sample from the distribution, and then you see the confidence interval happening here, which means that as we are, okay, so this is the actual ground truth. This is our forecast, and then the light blue region is the uncertainty that we predict, and we can see that we nicely lie within the uncertainty bar region, and the region increases as we go to the right. Okay, so here's the model in a little bit more detail. So we have a prior distribution. So this is a sequence model over time. So we go, time progresses from left to right. And there is a prior distribution over weights, which is PW. We can draw a sample from the prior. And we have a sort of a step function here, which gets the probability of a particular state given the previous state and given the parameters. And so that's the step we take, and then we do it again and again. And so that model is given as the P of the sequence Y, as well as the parameters W over the sequence. And that's the product of the probability of a particular state given its entire past. So we make it sort of general that this Y can depend on an entire past, plus the parameter drawn at that particular time, P of YT, times the prior WT. Okay, so that's that model. That's the prior model, in fact. And then there's the posterior model, or the variational posterior model. That's the model that we actually will, it's kind of is the model after learning when we incorporate the data. It has the same kind of shape. And here's the posterior over the parameters. And instead of here using the prior, now we're going to use this posterior distribution, Q. And that's a distribution that is now not drawn from a prior, but it is drawn from a distribution over these parameters, given all the state variables from the past. So you can give the entire state sequence from the past, and that gets you into, it's a function that maps to this posterior distribution for the distribution for this parameter, which we then draw, and then we can have, according to this rule, in fact, Y from the entire past, not just the previous one, but the entire past, will give you the new state Y t minus 1. And again, this is the elbow or the bound that we need to minimize, which is an expectation over the posterior, an expectation over time of the likelihood, which is this term, minus the KL between the posterior and the prior. That's the typical bound that we need to optimize in order to learn what the Q is. Okay, now some more details on the variational dropout model. So what I've said so far was actually completely general and nothing new actually. But now we're going to make a few choices, and those choices are driven by the fact that we want to come up with a good prior, which is not easy to get one in a high dimensional space of parameters. And we want efficiency. And I said this variational dropout that I mentioned before will give us this efficiency. And so what we're going to make, so we're going to make the following choice. We're going to say that the parameter omega at level L at time t is basically the product of a fixed matrix omega that we will use everywhere times a factor alpha, which will be given by a neural network. So here's a neural network F, depending on its own parameters delta, and gives as input the entire past sequence. That gives us a time-dependent multiplicative factor alpha t at level L that multiplies this matrix. And the randomness is coming from multiplicative noise, and that's quite special. Typically, people consider adding noise. So this is actually multiplicative noise, where epsilon is drawn from a distribution, a normal distribution. And because it is multiplicative noise, which is what people have figured out dropout really looks like, you get a posterior distribution over parameters omega given the entire past sequence, that has this form of a Poisson distribution, if you wish, where the variance is proportional to the mean, right? So in other words, for bigger values of the parameters, we're going to be more uncertain over those parameters. And that's, typically people say this is a fixed value sigma or something like that. So here the variance scales with the mean. And so that's special, but that also happens to work quite well, and it happens to simulate dropout, and it can be made very efficient. Okay, so then we move to the prior. So now this is a very special choice of prior, and it's kind of weird. It's called what we call it's a variational mixture prior, and what we do basically is we say, well, we actually know what is the perfect prior. The perfect prior is actually what's called the aggregated posterior. So we can express the prior as a, in terms of its posterior. And now any Bayesian will scream because you should pick your prior completely independently of anything else. And so this is something that a computer scientist of a machine learning person is more comfortable doing than a Bayesian statistician, because of course you're now already going to put information about data into your prior, which is really not what you should be doing. But it turns out that this choice is a very convenient one, and of course at some point the proof is in the pudding. You have to try it and see how well it works. But we do cheat a little bit in the sense that we express the prior in terms of the posterior. And it turns out that the ideal prior is in fact the aggregated posterior, which is the integral over all sequence or past sequence of py times the q of omega given y. So that's a prior that we're going to pick here. And of course, now we're going to stick this into the elbow, into the bound, and see, and then a whole bunch of terms are starting to cancel. If you do it, in fact, you can show that the prior over at layer L at time t is given by exactly the same shape as the one we have for the posterior here. And that will help us enormously in simplifying the elbow, and will help us enormously in creating an efficient procedure for inference. And so that's why it's sort of an opportunistic choice in some sense, to help us make sure that the procedure is very computationally efficient. I also want to mention that the parameters that we have are sort of shared parameters omega across all of the layers. And there's an independent set of parameters delta, which go into these terms alpha, which multiply omega here. They're both layer and time specific. So these are parameters that are layer and time specific, but they multiply this overall matrix omega. That's a choice. And it helps us being efficient, and it also helps us, I would say being time dependent, but not completely time dependent, but having sort of a core that is time independent and layer independent. Okay, so that was the theory. So I hope you sort of are with me until this point. So now we can go a little bit more into some applications. Now here is a model for PDE simulations. So in the PDE, you have a state of the system, and you want to predict the state the next time point. And so the model that was used here for the likelihood is a normal distribution of some mean function that depends on the previous state plus a set of parameters and a standard deviation, and then this goes into the entire posterior to compute posteriors, etc. And so you then use this to estimate the next state. Now, of course, we do this in a Bayesian sense. And the other one, which is actually a very general class of models, which are RNN, recurrent neural networks, and there's many instances of those. For instance, LSTM is a great instance. And so those are models of the kind, the P of y at some time t, the state, given the past plus the parameter, is some kind of function, it's a softmax function of some function h, which is you could call the state function, of time t minus 1. And then the state function is an RNN, which is a deterministic function which depends on the previous state. It depends on the h function of the state before, and it depends on the parameters. But now what's important is that, so h is a deterministic function that sort of collects information over time in a deterministic way. So you can have really strong correlations that go all the way back to the beginning because this is a deterministic function that sort of collects information. And so this is a very general setup. And for instance, one place where you're going to apply this is to molecular sequences like these SMILE strings. Okay, so then here's some results. Now this is the 3 PDEs, 3 one-dimensional PDEs. And we look both at the error, root mean squared error, over time, as well as the negative log likelihood, which is which will get hurt a lot if you predict the uncertainties incorrectly. And you see that some of these models, for instance, refiner, and what the other one, no, what's an ARD, they can get very bad in terms of this uncertainty prediction. You can see here, but they might still be, they might still be pretty good in terms of their RMSE. So it looks like they're making great predictions, but their uncertainty calibration is actually very poor. Where other models, and in particular BARNN, of course, is the one that we propose here, is very good. And here's some more sort of numerical values, negative log likelihood. And so this is a measure of calibration of the error. And so this number needs to be low if you want to be well calibrated. And compared to a whole bunch of other methods out there that try to, do the same, look at uncertainty as well, the BARNN model is actually very good. And I want to emphasize it's efficient. And so here we see basically for a particular PDE, the Kuramoto-Shifarshinsky PDE, you can see as it runs over time that as over time, of course, the uncertainties gets bigger, but you can see that the predicted uncertainties, which are the blue regions, especially let's say here, nicely calibrate with the actual error that is being made. And of course, that's precisely what we are asking from these models. And here we have a bunch of models where we, of course, in these models, we can increase the number of samples that we're drawing within our procedure in order to increase sort of the our let's say confidence in the error prediction. If we do a single sample, the RMSE is going to hurt. But as we are going to increase the number of samples, the precision is going to be very good. In fact, the map estimate, you can also do a very efficient map estimate, is actually always very good anyway. And here is a algorithm. Here's an example in molecular generation. When you do molecular generation, you typically want a high validity, which means you create correct molecules. You want a high diversity, which means you don't want to generate the same molecule all over again. Novelty, which means that it shouldn't be in your data set. And uniqueness, I guess, is another measure of not copying the same thing. And then, so you want to score high on all of these, and you can see that compared to LSTM, previous LSTM models that were trained on SMILEs, BARNN actually scores very highly. Plus, it has, of course, the benefit of this uncertainty. So here's another graph which shows the number of errors it's making on particular kinds of types of molecule bits and pieces from these molecules. In particular, rings are quite hard. These benzene rings are quite hard to predict well from these because they represent long range correlations in these SMILE strings. And as particularly for these long range correlations, you can see that BARNN is very good. Actually, I don't know precisely why it is so good for long range correlations, but it is. And then here we can see the number of molecules when you're generating. It's also generating sort of more complex molecules. So the larger you go into the right, the more complex the molecules are. And then sort of the shaded area tells you the total number of structures you're generating of these more complex molecules. And then the solid bar gives you the number of valid generated structures. And you see the more complex the things you generate, the more errors you're going to make. But definitely BARNN is still very competitive here, or most competitive. And then finally, here is some property prediction problem that we're looking at. So here are all sorts of properties of a particular molecule that you may want to predict. And sort of you see here the distribution of these properties of things that are generated by the algorithm versus the things you're predicting, versus the actual ground truth distribution of the molecules. You can try to compare those, and here you can see that the things that are being generated match very nicely with the actual marginal distributions of those over the actual molecules in the data set. And again, we can compare to SMILE's LSTM and LSTM, and we see that we compare quite favorably on all of these. And this is a two-dimensional map. It looks like there's a lot of structures here which are actually not in the regions where the actual molecules are, which are the blue ones, but most of the things are below the blue lines here, so it's a bit hard to see. But typically, this actually is pretty good. Most of the stuff we're generating is in the regions of where there is actual molecules. And I think that is we're now coming to the conclusions. Maybe I'm a bit early. I'm not sure. So the I think the most important thing is that we do see a revolution in the way, or a paradigm shift in the way that sort of we are doing science, in the sense that we are now adding all these computational tools like computational science, high performance computing, machine learning, and in the future quantum computing. And so those will have an impact on the way we do molecular science. And then there's, of course, also beautiful applications in sustainability, energy, and health. But these things are not going to fly without uncertainty quantification. That's very important to realize. And so we need to put more work in uncertainty quantification when we want to be successful in using these methods, and convincing, I would say, the scientists to use these methods in their domains. And so we've developed this BARNN model, which is a variational Bayesian method for sequence models. It is efficient, accurate, and has good uncertainty quantification. And then finally, we are currently working in predicting and using these same methods for LLMs. Of course, there's a huge space and a lot of excitement around LLMs. And hopefully we can make these chatbots, if you will, self-aware of their own limitations, so that they know what they don't know and they stop hallucinating confidently. And I think that is the last slide, and I will end there. Thank you.